Okay, so here we are with this. Welcome everyone. Um, thank you all for joining us today for the HMSC Research Seminar. My name is Yi-Chung Chung. I am the Academic Program Manager at Oregon State University's Hatfield Marine Science Center here in Newport, and I'll be your host of today's talk. A couple things I want to do before that is to go over some logistics. We have your mics, cameras, and screen share off, and we ask that you keep them off for the event. Please ask any questions you might have using the chat box found at the bottom or the top of your Zoom screen at any time, and we will answer any questions at the end of this talk. We'll be recording this event, and it will be posted in a few days on the HMSC websites, past seminar page, and I am putting that right there in the link now in the chat, so you can see that. And a couple announcements I want to make for next week's seminar. Next week's seminar will be Max Nielsen Pincus, Associate Professor of Environmental Science and Management, Portland State University, and Keegan Scully Engelmeyer, PhD student, School of Environment at Portland State University. We'll be talking about public perceptions of coastal resources and marine protected areas, exploring drivers of support and values for Oregon marine reserves. I also want to remind everyone that the virtual Marine Science Day is this Saturday, April 10th from 10 to 2. Please join us and see what the HMSC researchers have been up to this year. Our next Science on Tap is scheduled for April 20th with Vera Trainer from the NOAA's Northwest Fisheries Science Center, talking about harmful algal blooms and if they are getting worse. Finally, I want to add one more announcement, which is the Hatfield Student Awards and Scholarship Information Meeting. The last one will be following tonight's seminar at 5 o'clock. Deadline for the applications for awards is April 13th. And I am going to add the link to that page for anyone who needs to get the Zoom link for that talk, that presentation information meeting. So if you need any more info or the links to our upcoming events, check our HMSC homepage and scroll down to the bottom for more details at hmsc.oregonstate.edu. Now, for our main event, a little background on today's speaker. James Watson is an assistant professor with the College of Earth, Ocean, and Atmospheric Sciences at Oregon State University. He got his bachelor's degree in biochemistry and molecular genetics at University of Bristol. His master's degree in oceanography at the National Oceanography Center in Southampton University in UK, studying the phytoplankton evolution. And he received his PhD in marine science at University of California, Santa Barbara, California, working on ocean connectivity and near-shore marine species populations dynamics. At OSU, James studies the structure and dynamics of complex systems ranging from ecosystems to financial markets to the earth. He runs the Socio-Environmental Analysis C Lab at OSU, where he and his students are dedicated to advancing knowledge and understanding of people and our planet to help communities prepare for the coming challenges that they will face this century. Super excited about this talk, and here we are, James.
Thank you, Yi-Chung. That was a great intro. Thank you so much. And yeah, everyone, I'm really glad to be here. It's been a while since I've given a talk at Hatfield. Sorry I couldn't be in person, but I'm really thankful that we can still be online, and I have this opportunity to tell you guys what my lab and I have been up to. Okay, so where are we? Let's start here, right? So we live in the Anthropocene, the age of human dominance and influence over our planet. But what does this mean for us? Well, so the Anthropocene is amazing, right? We can do wonderful things. We've built megacities. I can get whatever I want delivered to my doorstep. Pre-pandemic, I was able to fly around the planet. I can watch an ungodly amount of online media. I can talk with my collaborators from around town and around the world. I can eat food from around the world, and yet students from around the world come to study with us here at OSU. Now, the Anthropocene is characterized by ever more connectivity. So, and as a result, our lives and our world is more and more complex. So this connectivity is in our social networks, our transportation systems, financial institutions, and so on. So this growth in connectivity has expanded the spatial scale of human interaction and influence. And last, the Anthropocene is characterized by its speed. So both in terms of the speed at which technological innovations are created, and also in the speed at which contagious things like information or disinformation and diseases spread. So while amazing, the complexity, scale, and speed of the Anthropocene have their downside. The social media that we use is having negative impacts on our mental health. Plastic trash has been found both in the deepest part of the oceans, so the Mariana Trench, as well as the top of Mount Everest. And we're converting the majority of the Amazon rainforest into soy farms. Financial institutions are creating more, not less risk, it seems, and diseases are spreading globally with more frequency. And last but not least, climate change is starting to bite. So how are we to adapt to all of these changes? Because they're not going to stop, actually, right? The COVID-19 pandemic won't be the last, and social media isn't going to disappear, and climate change isn't going to stop at some politically motivated time horizon like 2050 or 2100. We're very much living in a non-stationary world where there is no such thing anymore as normal. So again, how are we to adapt? So in this talk, I'm going to, while I'm broadly interested in all of these questions, I'm going to focus this conversation on marine environments. And I'm going to talk to three topics. The first is the emergence of novel marine environments. Second will be an introduction to fisheries connectivity, which is an important part of coastal community resilience. And last, there'll be an introduction to work we're doing on modeling the spatial distribution of international fishing fleets and how things might change in the coming decades as climate change alters the productivity of the oceans. Okay, so first up, this is a story about how new marine environments are emerging throughout the world's oceans. This work is the brainchild of Stephen Johnson, a PhD student in the geography program in CEOAS. Stephen is finishing up his PhD in my lab, and this is a large part of his dissertation. And I'm happy to say Stephen will be moving to ASU to start a postdoc with Mary Donovan in the fall. Some of you who may know Mary. So Stephen and I do a lot of reading about climate change, like many of us, right? And we're very familiar with these kinds of plots. Time series of temperature anomalies as estimated by Earth system models on the bottom left, and on the bottom right, like global maps of the same quantity at some point in the future. We acknowledge that these maps are obviously important, right? But they can be, say, a little abstract sometimes. And Stephen and I wanted to develop new measures of climate change that better captures the, say, lived experience of future generations. So we started focusing on specific places. And we decided to look at the world's large marine protected areas, MPAs. So here's the forecasted sea surface temperature time series for the Palau National Marine Sanctuary for three shared socioeconomic pathways, or SSPs. One thing that is often reported is the change in the average temperature, as illustrated here in these shifting distributions. That's useful, but no one actually experiences the mean, right? It's a time integrated statistic. Now, in addition to the mean, though, we also report on changes in extremes. So here we can imagine reporting on the change in the max temperature experienced at a given place here, in this case, Palau. So I think this is a little bit better than the mean because it really gets to some sort of visceral experience of climate change. What is the hottest it's going to be, say here in Corvallis or in Palau? But what we really wanted to get at was a metric that captures shifts in the familiarity of a given dimension of climate change, something that encompasses the whole distribution, not just a given moment, not just the mean or the 95th percentile, the whole distribution. So consider this cartoon, a temperature probability density function, right? So temperature on the x-axis and the probability of that temperature on the y-axis. Climate change is going to shift this distribution to the right. It's going to get warmer, right? The mean and all its moments move to warmer values, and so on and so on. Now, instead of simply measuring the change in temperature, like I've described just now, we use a metric from information theory called the Hellinger Distance to measure how much information is contained in one distribution relative to another. In this case, the cool blue baseline, right? So as the temperature distributions shift to the right, the overlap with the cool blue distribution diminishes and the Hellinger distance goes up until at the point where there is no overlap between the distributions and the Hellinger distance is 1. So this is how we measure the novelty of marine environments. Essentially, when the Hellinger distance is greater than 50%, there is more new information in the shifted distribution than not. So for those of you who might be familiar with these kinds of metrics, the Hellinger distance is related to the Kullback-Leibler divergence and the Jensen-Shannon distance, which are used in statistics for comparing distributions. Okay, so what does this actually look like, say, for Palau? If you look in the top left panel, we're overlaying the near future temperature distribution for the next decade, 2015 to 2029. So these are the color distributions for different SSPs, shared socio-economic pathways, on top of the distribution for the recent contemporary period. That's the distribution in light gray in the background. So what we can see is that in the next decade, things are going to shift a little. Things are going to warm a little because this is climate change. But the point is the Hellinger distance, our measure of novelty, is going to go up. And these values here are in terms of percent. Now, look to the bottom right. So this is now, we're zipping over to 2090 to 2100. What we can see is the color distributions have all shifted to the right. So there's a departure from the contemporary distribution, again in light gray. And as expected, the Hellinger distance have also gone up. So they're now all above 50%, highlighting the emergence of what we're calling novel environmental conditions. Now, we don't have to restrict ourselves to just temperature, right? We can look at other dimensions of climate change. For example, projected changes in sea surface pH. So due to the surface pH being driven in large part by atmospheric carbon concentrations, we see a striking departure amongst the carbon emission scenarios, so the SSPs in green, purple, and orange. And when we look at the distributions, we also see a striking move to new environmental conditions, essentially as measured by Hellinger distance hitting essentially 100% in the middle of this century. So we've done this kind of analysis for a number of ocean variables, here shown on the left for a 2090 time horizon. These are the model data that have come from Earth system models. So there are some interesting spatial differences in where novel ocean conditions will arise, depending upon the variable. And averaging over all variables, we get an overall measure of marine environmental novelty. We call this the Ocean Novelty Index, or the ONO index. So no surprise here, it's the tropics that will be most novel in the future. But there are other ways that we can look at this information. We can simply count the number of novel dimensions, so the number of variables with a Hellinger distance greater than 50% in the future. And again, this it highlights that the tropics, but now also the Arctic will be mostly new at this time horizon. This multidimensional information can be represented for specific places. For example, the world's big MPAs. These petal diagrams do well at revealing the ways in which environmental conditions will be new for particular places. Now, while I like doing new stuff, what I've actually shown you isn't new. The work we've done leads off of work done on terrestrial systems. In particular, this paper by Fitzpatrick and Dunn did something similar for major US urban areas. And they actually created this really cool web app where you can click on a major urban area and it will draw an arrow to the nearest similar urban area in the future based upon environmental conditions. So for example, you can go to this app and you click on Salem and it will say in 2060, Salem's environment will look like Sacramento's, which is pretty terrifying or cool, depending upon who you are. Now we can do this too for the oceans. For any particular place in the ocean, like off the coast of Newport, we can calculate the Hellinger distance to all other places in the future. In this case, based solely on differences in temperature distributions. Okay, so it's not the full multidimensional calculation, it's just based upon temperature. So what this means is that in 2060, the most similar waters based on temperature distributions only are the areas with low Hellinger distances in blue. In this case, it'll be up in British Columbia. Now, with this information, we can also calculate the distance we would have to travel to go to a similar environment as now, here in the future. If we did this for all places, we could make maps that reveal how far one would have to go to experience a similar ocean as today for all places. So for example, in the right panel, as highlighted in the big blue box there, the fuzzy blue box, you would have to travel around, the results of this analysis suggest that you would have to travel around 100 kilometers from Newport to find a similar ocean environment as there exists today. All right. Most notably, though, are a few places in specifically the tropics and the Arctic where these calculations reveal something quite disturbing. You would have to travel an infinite distance, or in other words, in 2100, at these locations, there will be no analogous environment to those found in the tropics and the Arctic today. Essentially, these environments are going extinct. There is nowhere else on the planet that those environments are moving to. Okay, so in conclusion, through the use of a bit of information theory, so Hellinger distances and climate projections, we have made estimates of where new marine environments are going to emerge. We also know where present environments are going to shift. And we also know that for some environments, they are actually going to go extinct. There will be no future analog to them. And this has a ton of implications. It has implications for us culturally, those of us who have a cultural association with a particular environment, as well as, say, for the efficacy of MPAs, which have been designed for present day environments. All right. So with change comes risk. This is part 2. So the question is that now, how do we manage risk? And this is work that I started about 10 years ago with Jamil Samhouri at NOAA up in Seattle. And this continues today with the likes of Mary Fisher, who's a student at UW, and Keiko Nomura, who's a PhD student in my lab here at OSU. So in general, there are 3 ways in which we manage risk. We can avoid the hit if we are quick enough to move out the way. If we're strong enough, we can take the hit. And last, we can pay someone else to take the blow if we have the funds. Now, believe it or not, these pictures were inspired and described in some way by these papers on risk in fisheries. And what we've been focusing on, as well as many folks beyond our little group, is how fishers participate in numerous fisheries as a natural means of managing income risk. So this is like the opposite of the gilded trap, where certain fishers on the East Coast only worked in one high return fishery. In general, fishers don't do this. They work in lots of fisheries to smooth their income over the year, as it were. Now, one thing that was lacking from this conversation was a method for quantifying sets of linked fisheries based upon fisher participation. So this systems representation, i.e. one that doesn't focus on any one fishery, but looks at how they are all connected, was something we worked on and published on back in 2017. The take home from this analysis was that what we termed fisheries connectivity varies greatly along the US West Coast, indicating coastal communities also vary in their adaptive capacity to environmental and policy shocks. So what is adaptive capacity? Well, loosely speaking, this is the ability to take a hit, and given a shock to one fishery, fisheries connectivity describes how fishers can shift their effort to other fisheries to recoup lost revenue. So this is something Mary Fisher, Steph Moore, Sunny Jardine, Jamil Samhouri, and I dug into in this paper that we just had out in PNAS. So in this paper, we looked at how fisheries connectivity in various Californian coastal communities changed in response to the 2015 harmful algal bloom. What we found is that absolutely fishers shifted their effort into different fisheries. and that this restructured the fisheries connectivity of a given community. We also found that fishers adapted in different ways, depending upon who they were. So in particular, we found that large and small vessels differed greatly in their response to the harmful algal bloom, either moving to different locations or even stopping fishing for the entire season. Now, all of this work informs us about how people adapt to a shock, a perturbation. In this case, a harmful algal bloom driven by a marine heat wave. So this is an episodic shock, but it is a part of a bigger gradual shift in ecosystem structure driven by climate change, some people would argue. So one extra question that we're trying to answer is whether long-term changes in fisheries connectivity inform us about a community's ability to adapt to climate change. So for this work, as part of her MRM degree, Keiko Nomura worked with collaborators down in Scripps to analyze socioeconomic information for Baja, California, essentially time series of fish landings, here seen on the right for the regions shown on the map in the left. These time series span 2001 to 2015, and you can see that what people caught over this period has changed dramatically. This is also reflected in changes in fisheries connectivity for these regions, for these communities in Baja. So for example, here on the right panel, we're showing the network structure of connected fisheries in a particular region in Baja, in region 1. And what we're showing is that the network structure changes over time. So in the early periods, so 2001 to 2006, there is a diversity of fisheries, and that are where the overall connectivity is low, say. But over time, this region has seen an overall decrease in the diversity of fisheries and an increase in the connectivity of those remaining fisheries. So this has implications. So the implications of these network changes for coastal community adaptive capacity are still being explored, but in general, it's a very active area of research. In sum, we all have mechanisms for dealing with risk, and diversification is one of them, but not all diversification is the same, and fisheries connectivity is a case in point. We are observing fishers adapting to climate change through their fisheries connectivity, through changing the sets of fisheries that they participate in, but it depends upon what kind of fisher they are. This is going to be critical to figuring out how coastal communities will adapt in the future as more shocks come our way. Okay, rattling through these. So last up, actually, International Fishing Fleet Competition. This work is very much owned by John Woodall and Shannon Hennessy, two postdocs in the lab who have really taken this project in some very cool directions. So as environments shift, that's what I talked about in part 1. So will the distribution of living natural resources. This is happening on land. So for example, in the bottom left, this is in terms of tree species, as well as in the sea. As people adapt to these changes, so that's what I talked about in part 2, about fisheries connectivity, policy must also adapt, because if not, people may come into conflict with one another. And that's what this final talk is all about. So in the bottom right panel, this is a photo from the Cod Wars that was between Iceland and the UK a number of decades ago. And it represents the reality that nations can actually come into armed conflict with one another over natural resources like fish. Now look at us today, right? In particular, the militarization and expansion of Chinese fishing fleets. International relations theory points to something called femtorisks. That is the ability for relatively small, seemingly insignificant actions somewhere in the middle of the ocean, potentially spiraling out of control, creating large-scale geopolitical tension. This is one of the hallmarks of the Anthropocene. This is its connectivity in action. So this is the framing for this research. Ultimately, we want to be able to identify new sources of these fishy femtorisks. To do so, we want to answer 3 questions. Where are there lots of nations fishing in the same spot? Do these nations have a history of cooperation or conflict? And are changing ocean conditions squeezing more fleets into smaller areas? So, where do nations fish? To answer this question, we need data. And luckily, there's been a data revolution in this domain. Specifically, the location of the majority of the world's vessels through time have been mined from various data sources, including satellite remotely sensed imagery of vessels, from vessel night lights, and from vessel GPS coordinates, which are synthesized through the Autonomous Information System, or AIS. So it's thanks to NASA that my team has access to a range of these satellite data products for this work, and it's also thanks to Global Fishing Watch, who've been instrumental in this data revolution, specifically with regards to AIS. So these AIS data have created a step change in our ability to monitor illegal fishing globally. So here I'm showing you a screenshot from Global Fishing Watch's website of the buildup of fishing activity by Chinese vessels around the marine protected area of the Galapagos Islands, which happened last year. Well, let's answer a question with these data. How much do nations fish? We can use these AIS data provided by Global Fishing Watch to compute the global fishing footprint for each flag or nation. So for example, in the top panel, I'm showing you the spatial distribution of fishing effort in terms of log cumulative fishing hours between 2012 and 2016 for every place in the ocean. China fishes in every ocean, the North and South Atlantic, the North and South Pacific, the Indian Ocean, and the Southern Ocean. Indeed, Chinese fishing vessels operate in around 25% of the world's oceans, which is a lot, given that most of the fisheries productivity is concentrated to a few areas. But China's not alone in this, right? Here, this is a spatial distribution of Spanish fishing effort. Again, it is global, but with some very interesting differences. In general, when we look at the total area fished by different nations, we actually see that China is not an outlier. Yes, they fish the largest area of the oceans, but many nations fish to a similar degree. Japan, Korea, Taiwan, Spain, Russia, and even the US, for example. So let's relate these maps to one of our original research questions. So who is stepping on each other's toes, or to what extent do pairs of nations overlap in the spatial distribution of fishing effort? So up in the top left is the spatial distribution of fishing effort by the US in purple, China in green, and places where they overlap in yellow, where fishing vessels from these two nations have been found working in close proximity. We can see that for the US and China, there is a hotspot in the equatorial Pacific. For the US and Spain, there's again a hotspot in the equatorial Pacific, but also now in the North Atlantic. These spatial overlap maps are very informative, but maybe a little bit too simple. To gain a better quantitative understanding, we have leveraged metrics from Community Ecology. This can help us identify congested areas of the oceans, where there are lots of competing nations fishing in the same spot. First, if we treat nations as species and fishing effort like abundance, we can compute the Shannon diversity or flag diversity for a given oceanic region. Second, normalized fishing effort is simply the total fishing effort over all nations. So in terms of fishing hours, normalized divided by the total number of vessels. So it's like a measure of productivity. So first up, let's look at the total fishing effort, normalized fishing effort in terms of log cumulative hours between 2012 and 2016 divided by the total number of vessels. Here we can see perhaps a familiar map. Areas of elevated fishing effort can be found in the major upwelling areas as well as productive shelf seas. Productive fishing areas are also found in the open ocean, for example, the equatorial Pacific. What about flag diversity, fishing flag diversity? Here, we find maybe a similar looking map, but with some very important differences. There is less flag diversity in the coastal regions relative to the high seas regions, and this makes sense. Most countries restrict access to their exclusive economic zones. That's the 200 nautical mile buffer zone around our borders. And so it is the high seas areas that have the greatest fishing flag diversity. One thing we're exploring is the relationship between these maps and the spatial distribution of biological diversity, which you would think should be related, but maybe not. We haven't found that out yet. Now we haven't done any analysis. I haven't presented any analysis yet. We've just been plotting maps, but we are doing quite a bit. So I'm going to show you some of the analysis we're doing that leverages, again, Earth system model data to help predict how these metrics, normalized fishing effort and flag diversity, may change over the coming decades. What we've done is to put fishing effort and flag diversity on the left-hand side of a regression type equation, say. And then on the right-hand side, we've put a number of statistics that describe time integrated characteristics of the oceans. So using Earth system model output, we can compute for the contemporary period the average sea surface temperature and the average chlorophyll concentration, say. But we can also compute the standard deviation in those guys as well. Indeed, we do this, computing these moments, the mean and standard deviation, skew, kurtosis, say, for a large number of oceanographic variables here listed on the right. And we also throw in a number of control variables too. We put all of this information into a random forest model with tenfold cross-validation, taking care about overfitting. So to reiterate, normalized fishing effort and fishing flag diversity is on the left-hand side of the equation, and all those Earth system model data and control variables are on the right-hand side of the equation. In the case of fishing flag diversity, we make an extra step of binning flag diversity into broad classes. So changing it from a continuous variable into categorical, none, low, medium, and high diversity areas. The models do pretty well. The regression R squared and the classification accuracy for the fishing effort and flag diversity models respectively are in the 70s to 80s respectively. And for this kind of data, this is not bad. Now with these models trained, we can then use projected oceanographic variables for some future time periods, say 2030 to 2045 or 2070 to 2090, to model how fishing effort and flag diversity might shift under a given carbon emission scenario. In this case, it's going to be SSP1, relative concentration pathway 2.6. So let's see how the model does at predicting flag diversity globally for the contemporary period. As I said before, the model results are binned into these categories, none, low, medium, and high levels of flag diversity. And the spatial patterns map onto the empirical values I showed earlier. Now let's have a look at how things might change as the climate warms and the biophysical characteristics of the oceans changes. What we see is a marked shift in the spatial distribution of flag diversity. This is seen more clearly when we subtract future estimates for flag diversity from those of the contemporary period. And this clearly shows a shift in flag diversity to higher latitudes, say. Now let's have a look at normalized fishing effort. So that's the total effort over all nations, normalized by the number of vessels, here for the contemporary period. Again, because our models achieve some reasonable measure of accuracy, the spatial patterns of modeled normalized fishing effort captures the large-scale pattern seen in the empirical data. But let's see what happens in a few decades. By 2070, climate change will likely have altered the biophysical characteristics of the oceans such that the spatial distribution of fishing changes dramatically. There is in general an increase in fishing effort throughout the world's oceans, in particular a shift in the Pacific. These changes are highlighted again when we look at the difference in fishing effort between the future and now. And this really highlights a number of big projected changes. The model suggests that there will be an increase in fishing effort at higher latitudes, again, like flag diversity, but also regional shifts in ocean basins. So in the Pacific, for example, there is a projected increase in fishing effort in the east. So in sum, through modeling the spatial distribution of flag diversity and fisheries productivity using a random forest model trained on oceanographic data produced from an Earth system model, we estimated that flag diversity and fisheries productivity will decrease in the tropics in general and increase at high latitudes. And interestingly, this reflects what we know about marine taxa. Much work over the past decade or so has fleshed out predictions for and understanding of latitudinal shifts in marine species distribution. And this new work suggests that there will be a similar shift in fishing flag diversity and productivity. Now, why is this important? Well, now we can identify places with an increasing number of competing nations. These are the potential hotspots of geopolitical risk over fisheries, a common pool resource. And this is why I'm showing you a picture of Eleanor Ostrom. The solutions she worked on for fisheries management, for incentivizing cooperation, can directly inform forward-looking marine policies aimed at reducing conflict between nations over living marine resources. Just a last note, this is just a little part of the work that we're doing, and it's been focusing on, for those ecologists in the room, on alpha diversity of fishing fleets. In other work, Shannon Hennessy is looking at beta diversity of international fishing fleets. So that's about comparing pairs of places in terms of the sets of nations fishing between those areas. In addition, Shannon's doing some really interesting spatial behavioral analysis of fishing and fine-scale physical ocean features known as Lagrangian coherent structures. And I couldn't help myself, but this is one of the amazing figures that Shannon has been producing for us. So this is fishing overlaid on maps of Lagrangian coherent structures. If we had a whole day, I would go into this in much more detail, but I just wanted to show you this because it is mesmerizing. All right. How are you all doing? That was a lot. So let's wrap this up. I started this talk by discussing the complexity, scale, and speed of the Anthropocene. Another way that this has been said is that connectivity is risk. And I like to think of risk, indeed systemic risk, as dominoes, and if they're all stacked up. If one falls, they all do. And in a way, this is in part how our transportation, financial, and food supply systems are presently arranged. If there is a push on one domino, a perturbation in one part of the world, because of the dense and global connectivity of our world, this shock can scale up to have global impacts. This is true of the pandemic. This is true of financial crashes, and it could also be true of competition over natural resources like fish. I think there are two underlying challenges that we're being faced with. The first is that the technologies that we continue to advance are fast outstripping our abilities to keep up. So I'll put it to you this way. People are linear, right? What this means is that if you walk for 10 times 1 minute, you'll end up 10 minutes away. But this is different for technology. If phone tech doubles in speed every year for 10 years, the tech is actually 1,000 times faster after 10 years. So we're much slower than technology. But the true challenge is this. The true challenge is that that policy change is sublinear. That is, it takes forever to update policies or develop new regulations. So just take, for example, the old tech that we're still struggling to deal with, fossil fuel energy. We're still struggling to put in the necessary policies for effectively managing this technology. And this relates to the second challenge that we're being faced with. The problems that we have to deal with are collective action problems, those that can only be solved through cooperation or mutual coercion, mutually agreed upon, as Garrett Hardin would say. And this is why I'm again showing a picture of Eleanor Ostrom next to Garrett Hardin, because it comes down to whether cooperative solutions can be achieved to overcome the many tragedies of the commons that we are facing. It's important to recognize, though, that cooperation is actually humanity's superpower. This is how we have overcome some of the biggest threats to humanity's survival in the distant past and also the near past. And this is how we must overcome the threats facing us now and in the coming decades. In doing so, we can turn those grand challenges into opportunities for a glorious future. The end. Thank you very much. And I would love to field any questions that you may have.
Thank you, James. That was great. We do have an immediate question in the chat, and it was related to the fisheries connectivity. How do you measure connectivity between fisheries?
Okay, so I presented three actually. There was the paper in 2017 with Emma Fuller, and this was the early work that I did on this with that team. And then there was one by Mary Fisher. That was the recent one, and then one with Keiko. That paper's in review. The first two, so Emma and Mary, we followed the approach that Emma fleshed out, which includes quantifying fisheries as Metiers. So Metiers are a form of come from clustering catch abundance data. In trips based upon what was caught, essentially. And then there is a formula, we developed an equation that essentially counts the number of vessels that participate in pairs of Metiers. The stuff that Keiko has been working on is different, right? In Baja, even though the data was an incredible data set that's been put together by the folks down at Scripps, it didn't have the same level of granularity as the logbook data that we used for the work here on the West Coast. And so the best we could do was look at the time correlation between landings at places, at ports in Baja. So they are actually quite distinct, and they measure quite different things. But that's how we measured it.
Great. We have from Francis Chan. Thank you for a super stimulating talk, James. I'm wondering how to link network topology to adaptive capacity. If a network grows in connectivity, more nodes or edges, is the interpretation that fishermen are doing fine and adapting well, or does it mean that fishermen are having to try a lot of new fisheries because nothing is working out? Great question.
Yeah, awesome. Francis, awesome. I'd never thought about it that way, actually. The initial thought was this: if you have on one extreme end the gilded trap, right? You're in Maine, you fish lobster, that's all you do, right? There is one node and there are no other nodes, and there are no connections. It's great. You make bank, you have made bank, but as we've seen, right? If anything were to happen to that fishery, you're out of luck, right? Or it's hard for you to adapt because you don't have the gear, you don't have the licenses, you don't have the knowledge, and so on and so forth, with which to say, diversify and recover your lost income. So that was always the assumption. Then on the other end is like a highly dense connected fisheries connectivity network where I'm a super fisherman. I'm a generalist. In a way, you can think about this in ecological terms. I'm a specialist predator. I only eat one thing. I'm really good at it, right? It's great. When times are stable, this is great. But if times are random, stochastic, right? You actually want to be a generalist. You want to be able to eat a ton of different things. That was the motivation behind this. So you can see that in the fisheries connectivity. If I'm I fish, species X, but I also fish Y and Z, that suggests that I have the technology, the gear, the knowledge, the license to do so. So if anything would happen to that one fishery X, I can go into fishery Y and Z. Now, what you said, right? I've not thought about it. Maybe a highly dense, diversified network is evidence of a failure in a way. Maybe like fishermen are trying to work in different areas, but it's not working. I haven't thought that through entirely. There I think of course there's and this is kind of a vacuous statement, but it's important to say that there is lots more work to be done on this, right? Because in a way, if you're familiar with those papers, like the first paper in 2017 was just like, hey, here it is, fisheries connectivity, static, like a snapshot. And these second papers that have come out, Metiers and Keiko's, they're really getting at like, well, this is changes. This is a dynamic, evolving thing based upon individual fishers' preferences, behaviors, these kinds of things. And we're getting there. But I think the next step is to really understand, to develop a model. Not for the sake of developing a model, but really for understanding why and how fishermen change what fisheries they want to participate in, if they can or not, and for what reasons. And I think that will really shed light on whether what we're measuring in terms of network metrics offer a window into adaptive capacity.
Could it be possible that the other fisheries that aren't labeled in there could be undervalued in the model? So new fisheries because it's what you're showing is based on the current fisheries, but there may be new fisheries that have developed that we're not even about, right?
Totally, right? So just to reiterate what you're saying, Eugene, right? Like species range distributions are shifting, right? So we're anticipating like there are going to be these new emerging new environments, as Stephen Johnson's work has shown, and along with that, there should be emerging new fisheries. If I'm at this one place at Newport, there should be these new fisheries coming up from the south, and so you have this concept, this mental model in your head of this complicated network, and it's complicated enough, and it maybe describes how a fisherman might be able to adapt by moving from this present fishery into this other one. But you're spot on, right? That fishery might go and a new one might crop up. So you've got old nodes going out, new nodes coming in. That's why it's very like a dynamic thing. And I think that's a critical question to answer. What is the projected possible fisheries connectivity given shifts in species ranges? And then what does that mean for the adaptive capacity of fishermen? I mean, I'm going on a bit, but think about this, right? Like, we know that there's this old story now, like where we're basically seeing species move out from the tropics into the high latitudes, right? And so there's always this like cartoon in my head. It's like, well, what do you do if you're in the tropics? Does that mean there's not going to be anything there? Well, let's play with that, right? So maybe if you're a fisherman there, you like 20 years ago, you had this wonderfully dense fisheries connectivity network because you had lots of different species, lots of different fish to harvest. But if we go to the extreme and imagine all these these species distributions shifting to higher latitudes, one by one, those nodes are going to go until all of a sudden you've got like not many species left. So you should be, and I'm not up to speed on the ecology of this, but right, is there a diminishing alpha diversity in the tropics? Would you also then anticipate a diminishing alpha diversity diversity of fisheries that you can connect through your participation? I could go on, but
yes, yeah. Well, I do want to get to these other questions that are in the chat here. So thank you for answering that, though. John Chapman asks, aren't the extreme climate changes in the Arctic and equatorial regions of your earlier map do top the fact that the tropics will be hotter than ever before and the Arctic regions never as cold as they were? Any ideas on how total fisheries production versus cost of harvest price will change? That's
okay, so maybe two things there, which is everything's warming, right? So but what we showed was that, again, it's a bit of a mouthful, but like it was really motivated by a personal thought experiment with Stephen, who's here online, I see. But Stephen's from Saipan, and we were thinking like, okay, so if the Pacific's warming, like, where would you have to go to show your grandchildren or give your grandchildren an ocean experience similar to the one that you grew up in, right? I didn't. I spent my childhood like on the streets in West London, but Stephen spent his childhood swimming around in the Pacific. So there is this visceral experience of that ocean in terms of its temperature, in terms of the pH, in terms of salinity, and so forth. And so the question is like, where would he have to take his grandchildren in the future for them to experience a similar ocean environment? And if you are from the tropics, and if you're from the Arctic, that story is very sad because there's nowhere you can go. There is nowhere on the planet you would be able to go to give your grandchildren that experience because those environments are going extinct. Second question was about is there an overall increase in fisheries productivity and a reduction in the cost of fisheries? Is that right? So I've limited knowledge here. I have been developing and running models, and by me I mean like I've got friends who are the experts in this, but we've developed like global fish models, so extending the utility of Earth system models to incorporate fish, and we're using those models to explore the response of fish productivity abundances in response to climate change, and there was just some interesting results. Overall, we're actually seeing a decrease in the abundance of fish, even with disregarding human activity other than anthropogenic climate change. And we're seeing something called the pelagification. We're seeing it depends upon how big the fish is. We're seeing actually an increase in small pelagics, sardines, herrings, these kinds of things. We've called this the pelagification of ocean food webs. But a decrease in the larger fish and a decrease in the smaller characters out there. So it depends on who you are and where you are, of course. The cost, sure. I think there's a story there. Like basically that's one of technology. As technology increases, well, no, I won't say it's that simple. You would imagine that as technology improves, as boat technology improves, the cost of fishing might go down. But I would also expect the cost of gas to be going up, actually, in the coming century, for maybe two reasons: as the access to fuel, the production of fossil fuels, maybe diminishes, but also we're hopefully going to. I mean, this isn't my a personal hope, I guess, which is we'll see carbon markets emerge and to be a cost on carbon. Anyway, so that's so it's hard to say whether the cost of fishing is going to go up or down. Of course, it depends upon who you are, right? If you're if you're a transnational industrial corporation, yeah, the price has gone down because it's cheaper to run one giant super trawler than 100 small trawlers, right? But if you just own one vessel, maybe the costs are going to go up. Can't say.
John says, great presentation. And we got another question here from Lorenzo Cianelli. Great talk. How do you account for seasonality in the analysis of change of physical features of marine systems?
That's a very broad question. How do you account for the seasonality in the change of physical systems? So maybe Lorenzo, you can point me to which part of the talk this specifically addresses, because I mean, I guess what you're seeing is that in actually all of these, but very much so in the first analysis and the third analysis. So that's the emergence of novel environments and then the modeling of international fishing fleets. We aggregated everything across timescales, right? So we didn't look at. We ironed things out. We didn't look at the seasonality, shifts in seasonality. I did. So let me expand upon that just a little bit, right? So for it's clearly described in the first part in the emergence of novel ecosystems, right? So we take a 15-year chunk with intra-annual data and interannual data, and we just say, give me like of temperature, like give me the distribution. So it includes seasonality, includes El Nino. So we've got this broad distribution, say for the contemporary period. And we also take a 15-year chunk for some future period, and we get the full distribution. And that's what I mean by smoothing out, collapsing things down. We necessarily collapse things down into just a distribution. But within that are the seasons and the El Ninos and these kinds of things. There was one slide that I showed that explicitly, right? So that kind of work implicitly accounts for seasonality. There's one slide that pointed to an analysis that explicitly accounts for seasonality, and that's the modeling that Shannon's been doing. There's that cool movie of Lagrangian coherent structures with fishing overlaid, and in that the timescales of the analysis are much finer. These are the days. Instead of decades, we're looking at days. So it is an explicit modeling of time there. Thanks, Lorenzo.
Okay. Another question from Kate Richardson. Do you have any thoughts on how we can enable diversification and adaptation in fisheries while meeting management goals around sustainability? For example, the cost/availability of permits or quota on the West Coast seems like it can make it challenging for fishers to maintain diverse fishing portfolios, but limited entry is also an important management tool.
I mean, that's such a, that was an answer into itself in my mind, right? That's an obvious obvious question to ask. So it's really insightful that it was asked here, right? Which is, if we accept the conclusion, I don't even know if I concluded anything, but that if fisheries diversification aids fishers' adaptive capacity, can we just let, can we increase that? But then exactly as the statement was just made, like if that was laissez-faire, like, well, what would that mean for actual sustainable fisheries across the board? And do you need to manage that? I have not got an answer for you there. I don't know what that looks like. But other than it's wrapped into the few last slides that I showed, which is that I think policymakers have to, and I think this is true actually, but policymakers have accepted that policy has to change more quickly as the environment changes more quickly. We have to adapt, not just individually, but as institutions as well. And there are different flavors of institutions, policy institutions, that naturally are agile or not. And I think, for example, like catch shares, for example, can be quite agile. Maybe there's a form of interfishery catch shares that could be set up. I'm just making stuff up right now. I've not thought this through, but something that gives coastal communities the ability to trade and adapt in their own way while being somewhat constrained so that there's not a blowout in a path like total maximum sustainable yield in any one fishery, but allows them to sort of make their own decisions. They're free to adapt because individuals they'll figure it out. And that's a powerful thing, not to diminish, right? So I think giving folks the ability to adapt in their own chosen way while sort of constrained generally so that there isn't a collective tragedy is what's got to happen.
And that's a challenging question for all managers, because it's a balance. It's a challenging balance to diversify and adapt. So that's the whole adaptive management focus.
Mm-hmm. Mm-hmm.
Well, thank you. Great presentation, great questions. We've reached the end of the chat questions. If there are any folks online who would like to verbally ask a question, we still have a couple minutes left. I would welcome and invite that. If not, we can conclude with the seminar. Oh, looks like, awesome presentation, James. Great seeing you.
Thanks again. Thank you. And thanks everyone. Yicheng, thanks for running the show. Lovely to see everyone and have questions from you guys. I hope to be able to see you guys in person soon. Reach out if you have any questions. You've got my email.
Great. Everyone's saying great. Enjoyed your talk. Fantastic talk. Loved it. Looking forward to having you out on the coast.
Yeah, man. This is great. Thank you.
Thank you. Thanks everyone for joining us today.
I'm just going to hang out until we're the last, Yicheng.
You bet.
I feel like that's the way to do it.
Yeah. And, James, with your kids, I would recommend checking out Marine Science Day virtually.
Of course. Yeah. They're as adept at Zoom as I am nowadays. So it's kind of crazy. We were all really sort of not anti, but like quite cautious with iPads. But then like my kid's school was like, my 5-year-old, here, you need to be on the iPad 8:30 in the morning. It's like, what the hell's going on? So we've struggled with that.
Hey, I just wanted to follow back on France's question at the very beginning, where he's talking about the nodes, right?
Yeah.
So, the question about network grows in connectivity, but if you added more nodes or edges, that's better, right? Because you're diversifying.
Yeah. I think I agree. But maybe Francis was getting at: is there a cost to that? Is there like, you can imagine? I mean, this is the thing with a generalist species, right? You're a jack of all trades, and you're not a master of any, right? So that in a way makes you weak. You could be invaded and outcompeted by a superstar specialist. So maybe there are these, like, I get it, right? In my talk, I really presented like diversification as necessary. These are times of great change.
Right.
When there's a lot of like this change going on, it's good to be a generalist. But maybe you got to acknowledge that it comes with a cost as well. So that might be evident in the fisheries connectivity networks too.
Well, that's his that part of his question was also addressing that. Yeah, so folks would have to modify and adapt to be able to diversify their fishing to create these new nodes or these new edges.
Yeah. Yeah, and I guess like, I mean, well, yeah, I don't know. Yeah, yeah.